Hello. This video will contain these solutions for Stu Schwartz's step-by-step problems, numbers 24 and 25. I'll try to fit those solutions into this one video. Okay, let's see what we have here. The figure to the right shows the graph of f prime, so this is the graph of a derivative, of the odd function f. This graph has horizontal tangents at x equals 1 and x equals 3. It looks like that, all right. And the domain of f is -4 to 4, and f of 1 equals 3. Well, this only shows me from 0 to 4, but we can piece together some information here, I think, because we know it's an odd. The original function is odd. Now, if the original function is odd, I think we talked about this in class a little bit, maybe depending on which class you're in. If you think about an odd function, like, doesn't this look like the sine function? Well, the sine function is itself an odd function. We're looking at the derivative here of something that is an odd function. And if you think of all the odd functions you know, for example, I don't know, like y equals x cubed, that's an odd function. Well, its derivative is an even function, because when you take the derivative, it's 3x squared. That goes to an even function. Sine is an odd function, but its derivative is cosine. Its derivative is an even function. So if our original odd function f, if our original function is odd, then its derivative must be even, when even functions are reflections in the y-axis. So I'm going to go ahead and draw. That means the derivative of this, since this is the derivative of our odd function, it must itself be even, which means it's a reflection in the y-axis. So there's a bunch of pre-calculus going on there, thinking about that. I guess pre-calculus and calculus. But that does have to be true, okay? Pause and think about that. Think about some examples of odd functions and how their derivatives have to be even. Okay, now that we have this, for what values of x does f on the interval from -4 to 4 have a relative minimum and relative maximum? Well, let's see. Relative minimums happen when we go from decreasing to increasing. And since this is the derivative, it looks like right here I'm going from decreasing to increasing. So it looks like there's a minimum at -2, and then let's see, it's increasing still. It goes down to 0, but it's still increasing, right? It never crosses over. So increasing that whole time, and then we go here from increasing to decreasing. So that's a maximum at 2, and one of the things we have to understand is when we have functions defined on closed intervals, you got to think about the endpoints. So here at this endpoint, wherever the end of this function was, it immediately started decreasing until here, right? So this function just kind of cut off at -4. Since it immediately started decreasing there, this must have been like a relative maximum there, right? We'll talk about that again when we sketch the graph, but it had a max at -4 because it immediately started decreasing. And likewise at the end here, this one is decreasing, 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 decreasing all the way to here, so that must be a minimum. And I think how would we justify our answers? We could say something, this one is a minimum because the derivative goes from negative to positive, and likewise for all those. I talked you through the justification, but we would expect a couple of words there to justify that. But they would all be justifications, something like this, something about the derivative. Okay, on what intervals is the graph of f concave up? Well, let's see. A graph is concave up when the second derivative is positive, and since this is the first derivative here, the second derivative is positive when this is increasing. So concave up here here, and here, right? The second derivative is positive when the slopes of the derivative are positive, or in other words, where the derivative is increasing. So that would be from -3 to -1. By the way, the AP test doesn't care if you leave these closed or open. You can do either. From 0 to 1, and from 3 to 4. What's the justification? Because f prime is increasing, right? Which means that the second derivative, that means second derivative is positive. Let's see about here. See, find the equation of the tangent line to f at x equals -1. Well, on an odd function, if f of 1 equals 3, then f of -1 equals -3. Remember how that works? If f of 1 is 3, f of -1 is -3, because they split like that. So my point is the point -1, -3. And then looking up here, if the slope here at 1 is 2, the slope at -1 is also 2, because of the fact that the derivative of an odd function has to be even, right? So the derivatives have to be the same on both sides. Draw a picture of an odd function and draw some tangent lines and see if you can justify that to yourself. But it is true. So y plus 3 is equal to 2, and it's x plus 1. You leave it like that, put it in some other form, if that makes you happy. And then last, on the graph provided below, draw a sketch of the general shape of f of x, -4 to 4, which passes through the origin. It has to pass through the origin because it's odd, right? Stu Schwartz has thrown us a bone here telling us that it goes through the origin. He didn't have to tell us that, I think. That has to be true, but that does help a little bit. Well, I'm just going to pretend this is a sine function here. If this were a sine function, well, what has a derivative that's the sine function? Kind of thinking backwards here. Would it be cosine? Well, the derivative of cosine is negative sine, right? So I guess the derivative of negative cosine would be positive sine. So I'm going to draw something that starts at the origin and looks like a negative cosine graph. Something like that, right? Usually negative cosine graph would be down here, but we know that it has to pass through the origin, so it's shifted up like this. And then since it's an odd function, it has symmetry about the origin. So here it flips. Let's see if I can get it to look. Oh, it doesn't look too bad. Something like that. Right? That looks like a negative cosine graph. The derivative of negative cosine would be positive sine. And then this one is a positive cosine graph, and that has a derivative of negative sine. Happy days. All right. Let's try the next one. Number 25. So we've got this function. We want to show first that its derivative is that. Well, that should be easy enough using the quotient rule here. Let's see, that would be low d high minus high d low over low, low, and we got some simplifying to do here. I suppose there are other ways of doing this that has just one denominator, so There might be an easier way, but I'm going to stick with this because I started this way. Let's see, that's 18x to the fourth. Any other x to the fourth terms? Yeah, I think here I have a minus 27x to the fourth. So 18 minus 27, that would be minus 9x to the fourth. Then I have minus 3x squared. Oh, sorry, I've already used that term, haven't I? Sorry, plus 18x squared over 9x to the sixth. And then just simplifying that, 9 cancels out everywhere, and we get 2 and x squared. 2 of the x's cancel out everywhere, and I think that gets us to what we want. So sure enough, that's our derivative. Find the x-coordinate of the critical point of f and determine whether the point is a relative maximum, relative minimum, or neither. And I think I'll point out to you here something that easy to miss. This has domain all positive real numbers, okay? Only positive real numbers. So he's restricting the domain on this function. So let's see, where's the critical point of f? We find critical points where the derivative is 0 or undefined. So derivative of 2 minus x squared over x to the fourth, that would be undefined at x equals 0, but that's not in the domain, right? The domain is only positive real numbers. That doesn't include 0. So you don't have to include that. And also you might note that even if we did get that information, we'd have to look back at the original function and see here that the 0 is not in the domain anyway. So it can't be a critical point if you're not a point on the function. So let's set this equal to 0 then. Find critical points, that's where the derivative is equal to 0. If you have a fraction equal to 0, that happens when the top is equal to 0. And that happens at x equals plus or minus the square root of 2. But since the domain is just positive reals, we're only interested in the positive square root of 2. So that's the first part right there. So x equals the square root of 2. Now, is it a relative maximum, minimum, or neither? We got to do our little derivative test here. So plugging in points on either side, plug in 1 is less than the square root of 2. So plugging 1 into the derivative here, 2 minus 1 over 1, that's positive. And then plugging in something bigger than that, like 2, 2 minus 4 over, that's negative. So if it goes from positive increasing to decreasing, that must be a maximum. Why? Because the derivative goes from positive to negative. Right? Same justification that we used before. Okay. Find intervals where the graph of f is concave up. If we're talking about concavity, we should be looking at the second derivative. So let's find that. Second derivative of this function using the quotient rule. Let's see, that's low, d high, minus high, d low, over low, low. And let's see, if we're looking for intervals, I think we want to find where the zeros are to chop up the number line. So let's see if we can simplify this. So I have minus 2x to the fifth, and then plus 4x to the fifth. That would be 2x to the fifth. And then, let's see, that's that term and that term from those. And then I'd have minus 2. If this is too many steps, once you could break that up. But it does simplify to that, and then I can divide out x to the third and a 2 on the top. So that's 2 times x squared minus 4 over x to the 5th. After a little simplifying there. And let's see, so that means our concavities can be chopped up from at -2 and 2. Those are the places where the top could be 0. But I don't actually need the -2, because remember our domain is all positive real numbers. So let's pick points on either side of this. Like 1. If you plug 1 into this, you get 2 minus 8 over 1. That's negative. And if you plug a number like 3 in, you get, oh boy, let's plug it in here. That'll be more fun. You get 3 squared is 9 minus 4 is positive, so that's going to be positive. All right, you can plug it into whatever version you want. Usually the factored version is better or easier. So it would be concave down here and concave up here. So concave up from 2 to infinity. And I think our justification is in our work here. But you could say, because the second derivative is positive. Right. And last, find the value of x where the tangent line to f of x is parallel to the line y equals x. Well, parallel to this means slope is 1, right? So that means set the derivative equal to 1, right? We want slope to be 1. Well, our derivative is 2 minus x squared for x to the 4th. Set that equal to 1 and do some algebra. So we get x to the 4th, and then let's see, add that over to the other side. Doing a couple steps here, you can break that down, and then it's not quadratic, but it's in quadratic form. You can factor it like this. Would be plus 2 and minus 1. Well, this doesn't have any zeros. That'd be like plus or minus I square root of 2. Right? You can't find any x values that when you add 2, you square that. That's not happening. So this gives us plus or minus 1. But again, only looking for positive real numbers. So it would be at x equals 1. That's our answer. Why? Because f prime of 1 is equal to 1, right? We can check that right here. 2 minus 1 squared over 1 equals 1. That's true indeed.